right, so now we know how much mass is going through this turbine. Next step. Okay, so now I can calculate the exergy stuff. So what I'm going to do is, now that we laid down the land here for these guys, I can grab these two and I can subtract them, because I know the subtraction will be equal to the reversible energy, right? So I'll put these two guys down like so. I want to take one minus the other, so I'm going to do this over here and just say this is negative this whole guy, this whole term here. Okay, this difference is not this. This is exergy 1 minus exergy naught equals to all this thing, and this is all equal to the difference in reversible work that we're after. Right, so if we were to write this whole thing down, we would have, we want it in power, or do we want it in, power, or do we want it in energy? If we want it in power, I forgot the mass here. If we want it in power, we want it to do the mass flow rate on all of these guys. So we're going to get in power. If we want it in energy, we want to do just the mass, right? In that case, we want the, I forget if you want the power or the energy. Let's check part A. Reversible power. Okay, so you want something in watts. So let's go ahead and use mass flow rates there. Beautiful. So this is going to be, I'm going to take, the masses are all the same, right? Mass flow rate here, same mass flow rate here, same here, same here, same here, same here. I'm going to take them all to the outside of what I'm doing. So the reversible work I'm after will be the mass flow rate, 1 or 2, it's the same, doesn't matter. That multiplies the whole thing times the enthalpy 1 minus enthalpy 2. What else? The T naught that multiplies the S1 minus S2 plus V1 squared minus V2 squared Okay, so I'm just combining the terms, right? This term with this term, this term with this term, and this term with this term. Now, last but not least is, okay, how come I'm using 2's and not naughts? Well, they're the same thing, right? Remember that the difference between the two, where is it? Here. The difference between these two guys here is not that the enthalpy is different or the kinetic energy is different. The difference is exactly this energy that was lost due to the entropy, right? In fact, like we said right in the beginning, this is actually equivalent to T of the dead state minus the difference in enthalpies, right? So the difference between the two is not the enthalpy between these guys here or the kinetic energy. In fact, the same. The difference is only that entropy. Okay, so we have everything we need. As a matter of fact, we've calculated most of it. This we know to be 5.156. This difference here we know to be 900 and something, 976.4 that we did before to calculate the mass. T naught we know to be 298, right? 25 degrees Celsius, but we need it to be in Kelvin because of the units of the entropy. Entropy on state 1 we grabbed at 7 point, what was it? Grab it, well, the difference is going to be negative 0.526, and let's just check on the entropies before we move on. Okay, where are my entropies? Here, one is this is the entropy of states of the state 2, so this is 7.69, and the other one should be a bit smaller. Yep, 7.116, right? So that's the difference that we get the 0.5 from. That's why it's negative 2. Okay, so note how we have negative and negative, so this is going to be a positive number. It's going to sum to the rest of it. And then here we have the 80 squared minus the 140 squared. And so that everything is in the same unit, we're going to have to correct this here and include the 2000, right? So note the units, so before we do that. This from the table, this is just kilojoules per kilograms. This guy here is Kelvin, and this guy here is kilojoules per kilograms Kelvin. And this here, if we do it like such, we're going to get out of this kilojoules per, joules per kilograms, right? So therefore, we do 2000, so that we get kilojoules here. So then the units are all equivalent, and here we're multiplying by kilograms per second, everything. So what happens is the kilograms go away, the kelvins and kelvins go away, and we're left with kilojoules per second, which is kilowatts. Okay, so number-wise, we get the reversible work out of this guy is 5808.5. Okay, 5808.5 kilowatts. So we can go ahead and say this is, about 5.8 megawatts, right? So guys, remember that the problem in the beginning is telling us that this turbine outputs 5 megawatts, and therefore 0.8, about 800 kilowatts, is lost due to irreversibilities. That's our conclusion from this whole math of part A, right? This is the whole conclusion from part A. So if we want to know part B, which is like, okay, but therefore what is your efficiency, right? What is your second law efficiency? And then you're asking literally, okay, the second law efficiency is how much did I get divided by how much I could have gotten had I not lost anything due to irreversibilities. Well, we got 5 megawatts or 5,000 kilowatts, and we could have gotten 5808.5 kilowatts, right? So therefore, my efficiency, my second law efficiency, is 0.860810. So let's go ahead and say this is 86.08%. Okay. So then the final thing for this is also obviously the other answer I'm looking for, right? So just to finish this off, note that I've said from the start, right? The difference here between these two guys is due to the irreversibilities. And the irreversibilities are this term here, are captured, I should say, captured on that term there. So if I didn't want to do this whole thing around Exergy, the other way of doing it is like, okay, I know I'm getting the 5,000 out of my work, which is the blue part, right? Beautiful. And if I want to know what's the red part, then I just need to do my temperature of the surroundings minus the difference in entropies, okay? And we know that this turns out to be 298 Kelvin times 0.5, what was it? 26. Okay, 5.26. And guess what this number is? Well, this is equal to 808.5. Right? There might be some rounding there. 108.5. Actually, this is 165.56.8ish, and we still need to multiply by, so this is kilojoules per kilograms per Kelvin, and we still need to multiply this by the mass, right? So if you multiply by the mass flow rate, the 5.126, then it is the 808.5ish kilowatts. Okay, so you could have done this way too, right? Note that, it wouldn't save you that much time, because to be able to find this mass, you would need to use the first equation anyways. But instead of doing this last step in which we combine the two exergies, you could have done just, okay, I know it's 5 megawatts plus this term here, and this term here times the mass flow rate ends up being 800. So therefore, if I lost 800 in irreversibilities, I would have gotten 5,800 had I not lost anything. And the entropy were exactly the same, right? If I had an isentropic process. So I really hope this helped you out. This is, long question. It's hard to understand. There's a lot of concepts that go into it. Hopefully you were able to get it all. If not, as per usual, just leave questions down below. If this video helped you out, consider liking it, and we'll talk soon.